Hello everyone and welcome back. So through the past quite a few videos we've been discussing derivatives and some of their applications. Many of the applications of calculus depend on our ability to deduce information, right, facts about a function from information concerning its derivatives. So because f prime represents the slope of the curve, it tells us the direction in which the curve proceeds at any particular point. We've also discussed, in the last video, local max and min values, where we see the derivative being 0. The tangent is horizontal. So what we're going to do in this video is really just kind of summarize a lot of the stuff we've talked about prior, and then we're going to introduce some new information on how the second derivative gives us information about a function in particular. So what I want to do for the first couple of minutes here is revisit a concept that we discussed back in the beginning of chapter 3, which was when we had first developed the idea of an average rate of change becoming an instantaneous rate of change. That was the slope of the tangent that we were looking at. And from that concept, we would generate the graph of the derivative. So I just want to revisit that concept here and then spin the conversation backwards, which is going to be what we focus on in this section. If we have the derivative, what does that tell me about the function? But first, let's go in the standard direction. So on this Desmos graph, what I have here is the graph of some function, f of x. And what we're going to do is what we did back in the beginning of chapter 3, and let's construct the graph of the derivative. Now, if we remember, the graph of the derivative is created by plotting the slope of every tangent line. So I'm going to try to animate this a little bit here. So I'm going to plot the tangent line. So I'm looking at, this is about x equals 1/2. And if I plot the tangent line on the function, if I were to measure the slope of that tangent, that becomes the y value on the graph of the derivative. And you can see down here we're plotting that point on the graph of our derivative. So when x is negative 1/2, the slope of the tangent on our function is negative 13. Then if I move to the next value on the graph, let's say we jump to x equals negative 1/4 here, then now I draw the tangent on my graph. It is measured to be around negative 11.8 according to my Desmos graph. So I come down here to where y is negative 11.8 and plot that point. And we continue this process, right? If I jump to the next point, now I'm at x equals 0. I measure that tangent. That tangent is negative 10. And I come down here and I plot negative 10, and there's the next y value on the graph of my derivative. And we can see as we continue that, right, so this next slope is a little less steep. It's a smaller negative number. We plot that y value of about negative 8, and then we move to the next point of tangency, let's say, and then we move to the next point of tangency. So as we continue to plot each of those points of tangent, each of the slope of each of those tangents, we're generating the graph of the derivative. And what we talked about in the prior video was, in particular, horizontal tangents representing possible max or min values, right? We called those critical points. Anytime our derivative was equal to 0, that was a critical point, and it was a possible max or min value. There's situations where a critical point isn't a max or min, right? We discussed all of that prior. We'll revisit that again today. So anyway, through this construction process of plotting the slopes of every tangent, we can generate the graph of the derivative. So I just kind of continue moving through this quickly. I move to the next x value. Now I'm at x equals 2.25. On my original function, I now have a slope that's positive, relatively small positive number. I plot that slope, and then I continue to move. Now my slope is still positive, but a little bit bigger in comparison to the prior one. Continue plotting. And we notice right about here at this point, we have the steepest part of the graph between these two horizontal tangents. So there's a horizontal tangent here, there's a horizontal tangent here, and kind of about midway between the two, the graph is the steepest. And then as I move towards that horizontal tangent, over here at x equals 5, now I have another 0 on my derivative. So notice that, again, as I continue moving, now my slopes become negative, and I'm plotting a y value that's negative, a steeper negative slope, a steeper negative slope, and the slopes continue to get steeper, and we plot those y values. So by plotting the slope of every, so I should say by calculating the slope of every tangent, plotting that number as a y value generates the graph of my derivative. So we can see the green dotted graph here would be the derivative of my original function f. Now, even though in this example that we've just gone through, we took the slope of the tangent to plot the graph of the derivative, what we're really going to do in this section is look the other direction. We're going to basically say, what does the derivative tell us about the function f? So let's suppose we don't know what the graph of f looks like. What information can I gather from the derivative that tells me about the shape of the function f? So let's just summarize from this example, what we have observed in the past and what we just discussed. So again, if I'm looking at the graph of the derivative here, notice that where the derivative is equal to 0, that's a horizontal tangent on my graph. Now, if I move just to the left of that point, right, on this interval to the left of -2 in my domain, to the left of 2 in my domain, my derivative has negative y values. Wherever my derivative has negative y values, my function is decreasing. Again, that should make sense, right? If the derivative has negative y value, that means the slopes of the tangents were all negative. Therefore, my function's decreasing. If my derivative has positive y's, so in this example, if we look between 2 and 5 in the domain, the y's on my derivative are all positive. When the derivative has positive y value, that means the function is increasing on that interval. So between 2 to 5, my derivative has positive y's. We can see the function increasing as x goes from 2 to 5. Again, in this particular example, at x equals 5, I have a critical point. The tangent has a slope that is 0, and the derivative is 0. There's the 0 on my derivative graph. And then as we move through that point, suddenly my derivative down here has y values that are negative. And that indicates that the function is decreasing on that interval. So any x greater than 5, my derivative have y's that are negative, and therefore my function is decreasing. Now again, the concept being here, if I turn off the graph of f, right, what does the information of the derivative tell me about that graph? So again, in summary, here's the graph of my derivative. Without the graph of the function, I know when x is less than 2, the derivative has negative value. My function would be decreasing on that interval. I know that between 2 and 5, the derivative have y's that are positive. My function would be increasing on that interval. And then I know when x is greater than 5, the derivative has negative value, and the function would be decreasing. So this is the conversation in this section, as I've said a couple times already. When we have information about the derivative, what does that tell me about the function in particular? Now again, a couple other things I want to point out, and I'm going to turn the graph of the function back on, is when my derivative changes sign. So let's take a look at this critical point for a second. So when I look at this critical point at x equals 5, the derivative was positive to the left. The derivative was negative to the right. So when I have a critical value where my derivative changes sign on either side, positive on one side, negative on the other, that indicates that I do have a local extreme value, either a max or a min. When I look back at this critical value, to the left of the critical value at x equals 2, right, to the left of that critical value, the derivative has negative values. To the right of x equals 2, that derivative has positive value. So because the derivative changes sign, that tells me I went from decreasing to increasing, and therefore I have a local, minimum in this case. So I paused the video real quick just to write down all the things that we just said verbally. So typically in a section of this nature and in a textbook that you're reading or looking at, here's going to be the information presented initially to summarize all of what we just discussed. So the first thing being that if the derivative is negative, right, if f prime is less than 0 on some interval I, then the function f is decreasing on that interval. If the derivative is positive, right, if f prime is greater than 0 on some interval I, then the function f is increasing on that interval. We know from the prior section, or prior video, that if f prime at some number a equals 0, right, then a is a critical point on the graph of f. If f prime changes sign as we move through that critical point, then there will be a local max or min at that critical point. Now again, just a summary of a couple of the things we discussed in the last video. We could have a situation, right, where we have a graph, maybe looks something like this, right? And we have a critical point at x equals a, let's say, and the derivative doesn't change sign. So notice in this case the function increases into that point. So my derivative would be positive, and then the function increases out of that point. So my derivative would still be positive. So since the derivative doesn't change sign at that critical point, we wouldn't designate that critical point as a max or min value. So feel free to pause this video for a moment to write this down to summarize all of the stuff we just talked about. Alright, so let's take the information that we just discussed and let's look at a problem that would be kind of a typical problem you might see in a homework out of a textbook. So in this problem we are given the graph of a derivative. We don't have any equations. We don't know what the original function f of x looks like, but we have the graph of the derivative, f prime. You're probably laughing at my graph that I drew here. It's not extremely precise. I didn't use gridded graph paper. I just want to focus on the general concept here. So based on the derivative of some function f, let's answer a couple questions. So there's three basic things we want to look at here. One is, where is the function increasing? Two is, where is the function decreasing? And then three, identify any local max or min values. Now, again, remember what we're looking at here is the graph of the derivative. So, if we're looking for where f is increasing, so first of all, if we're looking where f is increasing, so I'm going to scribble down here, I'm going to say f is increasing, and then we're going to fill in the blank in just a moment. So I'm going to give some intervals. So f is increasing wherever the derivative is positive. So I'm going to highlight for a moment where the derivative is positive. So the derivative is positive on this portion, right? All the y values are positive there, and the derivative is positive here as well. Now, wherever the derivative is positive, that interval, then the function is increasing on that interval. So what I'm looking at in this case is, as x goes from -1 to 2, the derivative has positive y values. So on the interval from -1 to 2, my function will be increasing. And then from 2 out to 6, my derivative has positive y values. So my function will be increasing on 2 to 6. Now, a pretty common mistake that I want to address here for a moment is, why did we split this into two intervals? Well, if we look right at x equals 2, the derivative is actually equal to 0. So I can't say the function's increasing at x equals 2 because the derivative is 0. The derivative has to be positive for the function to be increasing. So I really have two separate intervals where the function is increasing here. Now, where is the derivative negative? That is where the function is decreasing, right? So I'm going to go ahead and just scribble, say f is decreasing, and then we'll fill in the blank here. So the function is decreasing wherever the derivative is negative. So I'm going to pick a different color. Here's the first segment where the derivative is negative. So any x to the left of -1. So if I start at -1, I'm going to change color here so I can distinguish what I'm writing. So let me pick blue, right? Any x to the left of -1, the derivative is negative, and therefore the function will be decreasing. And then ditto, out here on the far right hand side of the graph, the derivative is negative again. So because the derivative has negative y's, then any x greater than 6, the function will be decreasing because the derivative is negative. So just from the shape of the derivative, we're able to deduce information about the function itself. Now the last thing we said we wanted to take a look at is where would we have any local max or min values. So again, we had said wherever the derivative changes sign, then the function will have a local extreme value. So I'm going to highlight in large, I'm going to draw that at this value of -1, my derivative was 0, right? That's a critical point on my graph. And the derivative changes sign. It goes from negative to positive as we move through that point. So -1 is a critical point, and it's going to be a local extreme value. X equals 2 that we discussed already, the derivative is 0. And therefore that's a critical point, but the derivative doesn't change sign, right? The derivative is positive to the left, and then as I move through that critical point, it jumps back to being positive again. So because I don't have a change in sign on my derivative, my function is not going to have a local extreme value there. And then the last place where the derivative is equal to 0, right, a critical point, is at x equals 6. And again, in this situation, notice that the derivative is changing sign as we move through that critical point. So I'm positive to the left, and then the derivative is negative to the right. So we have 3 critical points. So let's list the 3 critical points. So we have a critical point of the function f at x equals -1, 2, and then 6. So the way that I kind of like to write this, and we're going to get into this a little bit deeper in a moment, the way that I like to write this, I'm going to kind of think of like a number line, if you will. So I have -1, I have 2, and I have 6 as my critical points. What's the sign of f prime, and how does f behave, is what I'm trying to identify for myself. So to the left of -1, we had said, and I'm going to choose red as my color, right? To the left of -1 up here on my graph, my my derivative was negative, right? So that tells me my function is decreasing on that interval, like we already wrote. And then between -1 and 2, my derivative has positive y value. And we already said up here when we listed the intervals that my function is increasing on that interval. And then from 2 to 6, my derivative has positive value again. So my function's increasing, as we already listed. And then to the right of 6, my derivative has negative value. So my function is now decreasing. And again, I already wrote all that information down, but I'm a visual learner, and I like to visualize what I'm seeing there. So what we're seeing then is at -1, we're going to have a minimum value. We're seeing at x equals 2, we increase, we have a critical point, right? A horizontal tangent, and then we increase again. So there's no max or min value. And then we can see at x equals 6, we increase and then decrease coming out of that point. So I'd like to draw my little visual graph here so I can identify specifically where my local min and local max values are. So I'm going to go ahead then and summarize that and say f has a local min at x equals -1, and then f has a local max at x equals 6. So in this example, we took a look at having the knowledge of the derivative. Here was my graph of f prime. Based on the graph of f prime, knowing where f prime is positive, where f prime is negative, and where f changes sign, we're able to determine where the function is increasing, decreasing, or has a local max or min value. Okay, so I want to remind ourselves here that in a course like calculus, there's a couple things that we're developing, right? If we talk about course learning outcomes, one of the things that we're developing are our kind of knowledge mathematically. We're building up a concept base of how calculus can, help me, if you will. And in 2 ways, what we're discussing that is, one, the most interesting thing is in applications. If I'm looking at different applications, right, what can I do? How can I use calculus to help me within a particular application? Now, we've talked about finding local extreme values in the prior chapter, right? We talked about maximizing and things of that nature. So what we're going to continue to do here is develop our tools of analysis. Now, here's a function f of x equals x to the fourth minus 4x cubed. What we're going to do in this problem is ask, basically, where are the local max and min values? Where's the function increasing or decreasing? What are the critical points? Now, in reality, I could take out a graphing calculator and I could just graph this function and I can see where it's increasing or where it's decreasing or where it has a max or min value. But keep in mind, we are developing tools of analysis, so we want to pretend, if you will, that we don't have any graphing technology here. Now, even though we do, we want to do this work by hand. We want to do analysis utilizing our tools of calculus, and then we're going to come back, pull out our graphing technology, and check our work. The other thing we always want to develop these ideas without technology is there's going to be a day when the aliens invade. And notice I say when, not if. Now, when the aliens invade, they're going to challenge you to a graphing duel. And they're going to do an electromagnetic pulse, and they're going to render all electronics completely useless. And they're going to say, graph this function. And you're going to pass the graphing duel, this graphing test, and they're going to let you go free. And you're going to get to stay a free human being. All right, that's extremely silly. All joking aside, part of what we're developing in this course is our tools of analysis. So let's use what we just learned and let's do some analysis on this function. Now, I'm not going to write out the instruction, it takes too long, but let's talk our way through it. Basically, for this problem, we're going to find where's the function increasing, where's the function decreasing, and then what are the local extreme values, any max or min values. So in order to answer, first of all, where it's increasing or decreasing and where I have extreme values, I first have to locate the critical point. So just like we talked in the prior video. So we're going to say, what are the critical points? So that's where f prime is equal to 0. So for this function, what is f prime? So this is a polynomial. I'm going to use the power rule. So I'm going to have 4x cubed minus 12x squared, which is my derivative. And now I'm setting that equal to 0. So in this particular case, I can do some factoring. And I'm going to be left with x minus 3. Did I factor that right? Okay, I think that looks good. So now that I have factored, I'm going to set each factor equal to 0. Oops. And then this is going to give me x equals 0 and x equals 3. So I have two critical points on my graph. Now keep in mind, these may or may not be max or min values. They're just places where the tangent is horizontal. My slope is 0. So I need to further move along and test and determine which is which. Now, in the prior example, I set up kind of this number line in order to organize my information. There's a couple different ways to organize the analysis that we're about to attack. Some textbooks show you slightly different ways, and I'm going to show you the way that I like to because I'm a visual learner, and it helps me see what's really happening with the graph. So I'm going to write this just a little bit different. And I'm going to scribble kind of a number line. So here's my x-axis. And I'm going to plot my critical points. X equals 0 and x equals 3 are my critical points here. Now, what I want to do is test around these critical points. In other words, if I look to the left of 0, let's suppose I pick x equals negative 1, I want to know, is my derivative positive at that point or is it negative at that point? If the derivative is negative, when I plug in x equals negative 1, then I know my function's decreasing, right? If I plug negative 1 into my derivative and it has a positive value, then I know my function's increasing. So I want to plug this into my derivative initially. Now, the way that I like to organize this is the following. I'm going to look at each of the factors in the derivative. So I'm going to pick some yellow here. So when I factored the derivative, I had the factor 4x squared. So I'm going to come down here and I'm going to write 4x squared as a factor. And then I'm going to write x minus 3 as the other factor. So I'm just going to kind of scribble this below. And I'm going to plug negative 1 into each of those factors. And after I plug negative 1 into each of those factors, I'm going to determine what's the sign of the derivative. All right, so go with me for a second here. So I'm taking x equals -1 and I'm plugging it into my derivative. So I'm plugging it into each of those factors. So if I take -1 and I plug it into 4x squared, I'm going to get +4. Now the number +4 doesn't really matter to me, but the fact that it's positive is what's relevant. I'm only looking at the sign of the derivative. Now when I take x equals -1 that we're choosing as my test point, I plug it into the factor x minus 3, I'm going to get -1 minus 3, which is -4, so that's negative. So when I multiply those two factors together, positive times a negative is negative. And that tells me that my function is decreasing on that interval. So what I'm going to do up here is I'm going to say above my number line, what does f look like? So because f is negative, since f prime is negative, I know f is decreasing on that interval. Now I'm going to move to the next segment. So between my two critical points, between x equals 0, between x equals 3, I'm going to pick a test point. What can I pick? I can pick any number in that interval. I could pick x equals 1, or I could pick x equals 2, or I could pick x equals the square root of 2, right? Any number in there. I want to pick a number that's the simplest for me to plug into these factors. So I'm going to stick with integers if I have that option. So I'm going to pick x equals 1. I'm going to plug it into the factor 4x squared. That's going to give me +4. I'm going to take that x equals 1 and plug it into the factor 1 minus 3, into the factor x minus 3. So I get 1 minus 3, which is -2. So positive times negative is negative. Since the derivative is negative, my function is decreasing between 0 and 3, my two critical points. Now lastly, I'm going to pick a number to the right of x equals 3. I'm going to pick x equals 4, just because I feel that will be the easiest to plug in. So when I take x equals 4 and I plug it into the factor 4x squared, I'm going to get positive number. And then when I take x equals 4 and plug it into 4 minus 3, plug it into the factor x minus 3, I get 4 minus 3, which is 1. That's positive. So positive times a positive is positive. My derivative is positive, so I'm increasing on that interval. So the way I like this organization, the reason I use this process is I like the organization in a visual manner. So I'm answering a whole bunch of questions all at one time here. Apologize for that. I'm answering a whole bunch of questions all at one time here. I can now see where the function decreases. I can see where it increases. I can see where I have any max or min values. So let's go ahead and just write those things in sentence form and summarize what we found out. So we said f of x, which was x to the 4th minus 4x cubed, I'm going to say increases on the interval. Now, there's only one interval, otherwise I would say plural there. So it increases on the interval from 3 to infinity. So again, I'm looking at my critical point at x equals 3, and out to infinity, my derivative is positive, my function increases. So I'm increasing on the interval 3 to infinity. The function decreases on the interval. So we have two of them actually. Now remember, just like we talked about last time, I have a critical point at x equals 0. So my derivative is 0 there. My function doesn't decrease at x equals 0. So I have two segments, two intervals, right? So from negative infinity all the way up to 0, I'm going to have derivatives that are negative, and my function is decreasing. And then between 0 and 3, I'm also decreasing on that interval. And then last but not least, a typical problem in this nature would say, locate any max or min values. So now we can see quite clearly that at x equals 0, I'm going to decrease, flatten out, and then decrease again. So there is no local max or min value there. And we can see quite clearly at x equals 3, I'm going to decrease into and then increase out of. And we're going to have a local minimum at x equals 3. So just to finally summarize, we're going to say f has a local minimum at x equals 3. So this example illustrates if we have an equation for the function f of x and we want to do some analysis on the behavior of the function, without using graphing technology, we can take a derivative, and with that derivative, it tells me the behavior of the function, where it's increasing, where it's decreasing, where I have critical points, possible max or mins, and we can deduce whether those critical points are max or min values by looking whether the derivative changes sign through each of those critical points. Now, the next thing we want to discuss in this video is what information does the second derivative tell me about the original function f of x. So I wanted to come back to our Desmos graph just so we can discuss the concepts, see them in action visually, then we'll go back to our notepad and we'll do some examples. Now, from the beginning of this video, we had this graph f of x, the black colored graph, and then we had the first derivative of that function, the dotted line in green. Now remember, we had generated that dotted line in green going back to our conversation in chapter 3, plotting the slope of every tangent to generate the graph of that function. So what I want to do now, so to generate the second derivative, what I'm going to do is take a look at my first derivative and differentiate it. So I'm going to look at the slope of the tangent on this green graph, plot all of those slopes, and that then creates the second derivative of my function f. So I'm going to turn my function f off, and then what I'm going to do for the moment is turn on my tangent line. So here's the tangent line of my function. Now again, what I'm going to do, this is the derivative of the original function, and I'm going to find all of those tangent slopes. I'm going to plot them, and that's going to create the derivative of this function, which is the second derivative of the original function. So again, using Desmos here, I'm going to go ahead and turn on the graph of the second derivative. And there's the second derivative up to this value of x. We're at x equals negative 0.5. Now, as I continue plotting slopes of the tangent, we can see the derivative of the green graph. We're looking at the derivative of f prime, which is f double prime of my original function. Now notice right here, if the green graph is some function, it has a horizontal tangent at this value of x, so its slope is 0. So we can see the derivative of this green function has a 0 there. It's a critical point. Now, because this green graph is increasing up to that point, notice all the y values on this orange graph, right? Its derivative are positive. I hit a value of 0, horizontal tangent, and then as I start to move to the right of that critical point, the green function is decreasing, and now its derivative has negative values on its graph, negative y values. Now, what we just graphed here in orange is the second derivative of the original function. So I've turned off the graph of the first derivative, and I've left the graph of the second derivative. So what we're looking at now is the original function f and its second derivative. So what does the graph, or what information about the second derivative informs me of the behavior of the original function? Now, what I've focused the point on here for a moment is the 0 of this second derivative. And the 0 of the second derivative is corresponding to this point right here on the graph of the function. And I'm going to turn the derivative back on for a second. Remember that the second derivative has a 0 when the first derivative had a maximal value. What that's corresponding to on the graph of my function is the maximal slope of the function. So this is the point where the tangent is the largest, right? The slope of the tangent is the largest. Now, that is corresponding to what we call an inflection point. So here's what the second derivative tells me about. The second derivative tells me about the shape or the concavity of the original function. So if we notice, and I'll scribble this down on paper in a second, if we notice to the left of this value, right, the 0 of my second derivative corresponds to the steepest part on my function. If I move to the left of that inflection point, notice the graph looks like a bowl pointing upward, if you will. So this bowl could collect water. We're going to call that concave up. This is referencing the concavity of the graph. If I look to the right of the point where my graph has the steepest point, the graph looks like a bowl pointing downward, so it wouldn't collect water, if you will. So this point of the graph, or this part of the graph, we call concave down. So what the second derivative tells me is about the concavity of the original function. Notice where the graph is concave upward, my derivative has y values that are positive. Sorry, my second derivative has positive value. So what we're going to write on the paper for a moment is wherever the second derivative is positive, that corresponds to my function being concave up. Where the concavity changes will be the zero of the second derivative. And then when the function is concave down, my derivative has values that are negative. So if the first derivative tells me where the function's increasing or decreasing and information about local max or min values, the second derivative tells me about the concavity of the function, and any places where concavity changes direction, we call that an inflection point. I paused the video real quick just to write all of this down. I don't want you to have to watch me write this down. Again, feel free to pause the video here and scribble this in your notes. But in summary about what we just discovered or saw on our Desmos graph, if the second derivative is positive on an interval, then the function is concave up on that interval. If the second derivative is negative on some interval, then the function f is concave down on that interval. If f double prime at a is 0, then x equals a is a possible inflection point. And again, if f double prime changes sign as we move through x equals a, then there's a change in concavity, and we call x equals a an inflection point. So, for the first derivative, it tells me about increase, decrease, and if there's a change in sign of the first derivative, we have a max or min. For the second derivative, it tells me about concavity of the function. And at x equals a, if there's a change in sign of my second derivative, we're going to identify that as an inflection point. So the first example I want to take a look at here is again focusing on the more bigger picture concept here. What the second derivative tells us about the original function f. So without getting bogged down into algebra of equations, and here's a graph of f double prime, and we want to know what information can we deduce about the function f based on this knowledge of its second derivative. Now, I'm going to go ahead then again and list out my little, kind of number line that I like to write. And I'm going to say, what's the information about f double prime and what does it tell me about the function f? So I'm going to plot my critical points of my function here. Now, I didn't label this point, but this was intended to be -2, right? We can see that this is the origin, and this is x equals 2. So the possible inflection points are where my second derivative is equal to 0. So at x equals -2, I have the second derivative equal to 0. At x equals 0, excuse me, the second derivative is equal to 0. And at x equals 2, the second derivative is equal to 0. Now what I'm looking for, let me scoot this over to the left a little bit. So what I'm looking for, right, is concavity of the function. So where is the second derivative positive? Where is the second derivative negative? So first let's just discuss where the second derivative is positive. So here on this segment, the second derivative is positive. And then here on this segment, the second derivative is positive. Now, when x is less than -2, my second derivative is positive. And that tells me my function is concave up. And then, as x goes from 0 to 2, my second derivative is positive, so my function is also concave up on that interval. Now, between -2 and 0, my second derivative is negative, and I completely forgot one other interval. Let's come back and fix that in a second. So between -2 and 0, my second derivative is negative. So I'm going to use red. Between -2 and 0, my second derivative is negative, and I'm concave down. Now, I forgot that other segment of the graph. Please excuse me. When x is greater than 2, my second derivative was positive. Completely missed that. And therefore, when x is greater than 2, my second derivative being positive, my function is concave up. Now in this case, there's two places where we see a change in concavity. We see a change in concavity at x equals -2. We change from concave up to concave down. And then at x equals 0, we see a change in concavity from concave down to concave up. So I will classify those officially as inflection points, and we'll write that down in a second. So from this little number line that I like to draw, most textbooks call this the second derivative test. But I'm going to go ahead then and list the information we know about the function f. So I'm going to say f is concave up on the interval. I have 3 of them, so I'm going to say plural. So on the interval from -infinity up to -2, between 0 and 2, and then greater than 2. And I'm going to say f is concave down on, and we had the one interval from -2 to 0. And then we can say the inflection points are where the concavity changes. So we said that was at x equals -2 and x equals 0. So again, in summary, right, this example gives us the graph of f double prime. Based on that graph, we're able to determine where f double prime is positive, where it's negative. That tells me where my function's concave up or concave down. Once we can see where the concavity changes sign, then we can officially identify those points as inflection points. For the next example, I want to come back and focus algebraically on analyzing a function. So earlier we had looked at the function x to the 4th minus 4x cubed. And what we had done for this example was took the derivative and inferred where the function would be increasing or decreasing, where we would have max or min values. So I want to come back now and look at the second derivative. And the instructions for a problem like this might say something like, find the intervals of concavity for this function and identify any inflection points. So, in order to look for inflection and intervals of concavity, we need the second derivative. So I'm going to scribble down here, where is the second derivative equal to 0? So our first derivative we'd already done, but we can redo as 4x cubed minus 12x squared. So the second derivative is going to be 12x squared minus 24x. And we're looking for where that is equal to 0. So let's do a little bit of factoring here. I can take out a 12 and an x. I'm left with x minus 2 equal to 0. We can see setting 12x equal to 0 and x minus 2 equal to 0. We're going to get x equals 0 and x equals 2. So again, these are values where my second derivative is equal to 0. These are possible inflection points. What I need to do is test. So I'm going to take the same approach that I did with the first derivative. I'm a visual learner. I like to organize this in a particular manner. So I'm going to take a look at what are the values of the second derivative. What does it tell me about the function f? So I'm going to plot the two zeros of my second derivative. And again, I recommend, right, what I like to do is look at each of the factors. So the second derivative had the factor 12x, and it has the factor x minus 2. So I'm going to list information about each of those factors and say, what does that tell me about f double prime? So I'm going to do my test points just like we did last time. So to the left of x equals 0, I'm going to pick -1. Plug it into the factor 12 times x. That's going to give me -12. -1 minus 2 is going to give me -3. Negative times a negative is a positive. So I know my function's concave up when I'm to the left of x equals 0. There's my 0 of my second derivative. Then I'm going to pick a test point between 0 and 2. I'm going to pick x equals 1. So 12x, 12 times 1 would give me positive 12. And then 1 minus 2 would give me -1. So positive times negative is negative. My second derivative is negative. My function's concave down on that interval. And then last but not least, I'm going to pick something to the right of x equals 2. Let's pick x equals 3. 12 times x, that's going to be 12 times 3 is 36, that's positive. And then 3 minus 2 is positive 1. Positive times positive is positive. So my second derivative is positive, so my function's concave up. So from the second derivative, we can write some conclusion. We can infer information about our original function. So I'm going to say f is concave up on the interval. So I'm going to be from minus infinity to 0 and 2 to infinity, where my second derivative is positive. And then f is concave down on the interval from 0 to 2. And then the inflection points, I'm going to get lazy, PTS. The inflection points are going to be where my concavity changes sign. So as it turns out, at both of those values, x equals 0 and x equals 2, my concavity changes there. So I'm going to list both of those as being places where concavity changes. The next concept I want to look at here, pretty classical concept you'll see in every calculus textbook, is how can concavity tell me about whether I have a max or min value of a function. So I scrolled back up to this example where we looked at x cubed minus 4x squared. It was x to the fourth minus 4x cubed. And we first asked ourselves, where's this function increasing or decreasing, and what are the max and min values? So we took the derivative, we set it to 0 to find the critical points, and then I set up this line test to determine where the derivative changed sign. So again, wherever the derivative changed sign, those are max and min values, and from our little diagram here, we're able to determine which values of x, which critical points, contained max or min values. Now another approach to this is to consider concavity. So for example, I'm going to scribble over here on the right hand side. For example, I want to point out to you on this graph here, at x equals 3, we had a change in sign of my derivative. We went from decreasing to increasing. Now, notice in this case, and in all cases actually, that the concavity is upward in that case. So wherever I have a minimum value on my graph, its concavity is going to be in an upward direction. If pretend we had a local minimum on this graph, at that particular point on the graph, the function's concave down. So instead of setting up, so suppose we're only looking for max and min values and we're not looking for intervals of increase, decrease. If we're only looking for max or min values, what we really could do is take our critical point. We had x equals 0 as a critical point. I could find the concavity of the function, use the second derivative, and determine whether there's a max or min value there. I could take the critical point of x equals 3, determine that the second derivative is positive. So that means we have concave up and a minimum at that point. And then again, out at this place here, let's pretend it was x equals 7. Right? I could find the critical point, x equals 7, plug it into the second derivative. In this case, I would see second derivative is negative, function's concave down, and we have a local maximum at that point. So again, I paused the video to write this down. In summary, if f prime at a is 0 and we know f double prime at a is positive, then f has a local minimum at x equals a. I just scribbled the little graph to the right to illustrate that concept. If f prime at a is equal to 0 and f double prime at a is negative, right, again that means the function's concave down, so we're going to have a local max at x equals a. Now, if f double prime at a is 0, we actually have no conclusion. It could be a local max, it could be a local min, or it could be neither. We can't deduce any information. We don't know the concavity at that point. Now again, personally, I prefer to use that first derivative test, what we were just looking at a second ago. I prefer to just do the line test, determine whether function's increasing or decreasing. The reason that I like to do that is if we only take this approach and we encounter the second derivative equaling 0, then we can't draw a conclusion, and then we would have to go back to set up that number line to do that visualization of the problem. So personally, I prefer to just do that line test, and that way I avoid this no conclusion situation. However, if it's going to be kind of obvious what the second derivative is going to be in terms of sign, positive or negative, then you could jump to this and avoid some of that work in that line test. In this example, let's take everything that we have learned and let's piece it all together in one big question here. So in this problem, we're told that we are given the graph of a function y equals f of x. We want to determine at which point each of these groups of conditions are met. Right? So, number 1 says y prime, y double prime are both positive. Number 2 says y prime, y double prime are both negative. Let me fix that double prime there. Number 3, y prime is negative, y double prime is positive. And then number 4, y prime is positive, y double prime is negative. So let's just look at the graph. Let's just move left to right here chronologically as x increases. So point A, what's happening at point A? At point A, the function's increasing, so y prime is positive. But the function is concave down, so y double prime would be negative. So that puts us in number 4, y prime being positive because we're increasing, y double prime being negative because it's concave down. Now if we look at point B, the intention there is that it's at the local max of the function f of x. So for letter B, because we're at a local max, my first derivative is 0. And I don't fall into any of these 4 conditions because none of them say y prime would be 0. So we're not going to place letter B into any of these groups of conditions. Now if we look at letter C is on a point where the function is decreasing, so y prime would be negative. And it's on a point where the function's concave down, so y double prime would be negative. So point C is going to go into number 2. So y prime and y double prime are both negative. We're decreasing and we're concave down. If we look at point D, the function is still decreasing, so y prime is negative. But now the function is concave up, so y double prime is positive. So that would put us in number 3. Again, y prime is negative, we're decreasing. Y double prime is positive because we're concave up. Now if we look at letter E, the function's increasing there, so y prime would be positive. And then what is y double prime? Well, we have no concavity on that graph, and it looks like a linear function. So because there's no concavity, y double prime would be 0. And in fact, if you think about this momentarily, right, if we're looking at a line segment might be like y equals 5x. We take the derivative of 5x, we get 5. But then we take the derivative of 5 and we get 0. So the second derivative is 0 here. We have no concavity in this case. So point E doesn't go into either of these categories because y prime would be positive, the function's increasing, y double prime would be 0, which we don't have in either 4 of these. Alright, so this video is getting a little lengthy here. As you've heard me say many times before, I don't like for these videos to get too long. In a calculus course, that can happen. These examples get quite lengthy. So let's take a look at one last example. And what I want to do is come back to where we have an equation of a function, and we're going to find or deduce information about where the function is increasing, decreasing, do we have any local max or mins, and then intervals of concavity, and any possible or any inflection points. Now, I'm going to, in this example, pick the function f of x equals x squared minus x minus ln of x. Now obviously we could have a whole bunch of examples that we do. I mean, we could do like 10 different examples where we vary the forms of these functions. We could have a function that has sines and cosines in it. We could have a function that has an e to the x in it, or square roots, or hyperbolic signs, things of that nature. So we could have a video that's like 10 hours long where we take a look at a bunch of different scenarios. I just want to take a look at one more example, keep this video at a somewhat manageable length. So to find where the function's increasing or decreasing, any possible or any max or mins, we need to take a look at the first derivative. So let's take a look at the first derivative of my function. So the derivative of x squared is 2x, the derivative of negative x is negative 1, and the derivative of ln of x is 1 over x. Now whenever I have a fraction, the best practice here, so remember, I'm going to set f prime equal to 0. So when I set f prime equal to 0, the simplest thing to do is have one big fraction. I'm going to go ahead and combine all of these terms here. So, 2x over 1, 1 over 1, and then 1 over x. So my common denominator here is x. So the first term, 2x, I have to multiply by x over x. So I'm going to end up with 2x squared. And then that second term, negative 1, I'm going to multiply in the bottom by x and in the top by x. So that's going to give me minus x. And then I have minus 1. So when I set this equal to 0, right, the denominator really doesn't matter in regards to that question. Now, we haven't really done this in this section. And by this, I mean what we did in the prior video. When we're looking for critical points, we technically want to look where the derivative is equal to 0, and we want to find out where the derivative is undefined. And again, as a summary of that, the derivative could be undefined at a corner, and I could still have a local minimum at that corner. So we technically want to look for where the derivative is 0, the derivative is undefined. Those identify the critical points. Then we wanted to determine the relevance in regards to increase or decrease here. And the reason I didn't do that in the prior example is I had a polynomial, right? I had x to the 4th minus 4x cubed. There was never anywhere that my derivative would be undefined. It was a polynomial. So we have a scenario here where my derivative could be undefined. So let's make sure we include that in our location of finding critical points. So where does the derivative equal to 0? So if I look at having a fraction, right, the only time a fraction is equal to 0 is when its numerator is equal to 0. Now let's see if this factors. If this doesn't factor, we're going to use the quadratic formula. I think this is going to factor. Let's see if that works. So 2x times x would be 2x squared. Outside would be minus 2x. Inside would be plus x. That would give me my middle term of negative x. And then the last positive 1 times negative 1 would give me my constant term of minus 1 there. So this does factor. Setting each of these factors equal to 0, I'm going to get x equals negative 1/2. And then x minus 1 equal to 0, I'm going to get x equals 1. All right, now where is the derivative undefined? That's where the denominator is going to equal 0, and then x equals 0 is a critical point. Now, I'm running out of room on my digital paper. I'm going to go ahead and do my line test. So I'm going to set up my number line. I'm going to plot each of these critical points. So the first critical point chronologically was negative 1/2. We have negative 1/2. My next critical point is 1. Oops, my next critical point actually is 0, where my function's undefined. And then my next critical point is 1. So I need to plug test points into my derivative, and that tells me information about f. So my first critical point is negative 1/2. I'm going to take negative 1 and plug into my derivative. So if I'm going to plug into each of these factors. So if I take negative 1, plug into 2x plus 1, what I'm going to get in that case is negative 2 plus 1. So I'm going to have negative 1. I plug negative 1 into that second factor, and I scribbled that down wrong. Let me fix that. That is x minus 1 as the factor of the numerator. So if I plug negative 1 into there, I get negative 1 minus negative 1, which is negative 2. And then negative 1 in the denominator would be negative. So in the numerator I have negative times negative, which is positive. In the denominator I have negative. Positive divided by negative is a negative. So the overall sign of f prime is negative. So my function's decreasing on that interval. Now I need to plug a number between negative 1/2 and 0. I'm going to plug in negative 1/4. Remember, all I really care about here is the sign of my derivative. So if I plug negative 1/4 into the first factor, 2x plus 1, in my numerator, 2 times negative 1/4 is going to be negative 1/2 plus 1 is going to be positive. And then negative quarter minus 1 is going to be negative. And then negative quarter in the denominator. So in the numerator, I get positive times negative, which is negative. In the denominator, I have negative. And dividing those gives me a positive value. So my function increases there. And then between 0 and 1, I'm going to pick x equals 1/2. Plug it into the two factors in the numerator. 2 times x plus 1. So I'm going to have 2 times 1/2, which is 1, plus 1, which is positive. Plugging into the factor x minus 1, I'm going to get 1/2 minus 1, which is going to be negative 1/2. And then 1/2 in the denominator is positive. So positive times negative in the numerator will be negative. Positive 1/2 in the denominator. And when I divide those, I get a negative. And I'm decreasing on that interval. Last but not least, I need to plug something into the right of x equals 1. I'm going to pick x equals 2. Plugging into the numerator, I get 2 times 2 plus 1. That's positive 5. I get 2 minus 1, which is positive 1. And I get 2 in the denominator. All of that gives me a positive, and the function increases here. All right, now before I jump to determine where my function decreases, increases, and formally discuss that conversation, I want to make sure that I'm summarizing over the domain of the actual function. Remember, my actual function was f of x equals x squared minus x minus ln of x. So the domain of this function is governed by the logarithm, right? X squared minus x, those are polynomial terms, they're defined everywhere. The logarithm can only have positive values. So the domain here is x strictly greater than 0. So I'm not looking at any of those negative values. All right, so let's learn from the mistake that I just made here. The mistake that I made was I tested two intervals, which are completely unnecessary to test. I didn't need to test anything to the left of 0. I wasted some time there. So when we summarize where my function's increasing or decreasing, I'm only looking greater than 0. So let's say f is increasing on the interval 1 to infinity, right, where its derivative is positive, and then f is decreasing on the interval 0 to 1, where the derivative is negative. Now when I come back up and I look at my little line test here, let me zoom out of here, I would be tempted to deduce that we have a minimum at x equals 1. The way that I'm going to determine whether a minimum is there or not is I need to plug back into the function to see if it's defined there. Now it is going to be defined there. X equals 1 is in the domain. But we could have a situation where x equals 1 is a vertical asymptote. Right? Think about that for a second. X equals 1 could be a vertical asymptote, and it was one of my critical values. My function could change from increasing to decreasing at that vertical asymptote, but I wouldn't have a max or min value there. So I just want to be careful that when I'm testing whether x equals 1 is a max or min value, I just want to make sure my function is defined there. And in this case, it is. So the local min value is f at 1. So we have a local min f at 1. So in that case, that's going to be 1 squared minus 1 minus ln of 1. Remember, ln of 1 is 0. So I'm really getting 1 squared minus 1. And that actually turns out to be 0. So at x equals 1, I have a local min, and the minimum value is y equals 0. Right? And again, I'm just scrolling up back to my graph. Again, I'm looking at that segment there. At x equals 1, we're going to have a minimum value, and that value is 0. So if this is a homework problem, the pieces of information we might be asked is where's f increasing, where's f decreasing, and where are the local max or min values. So in summary, to answer those questions, there is the answers. Now, the homework problem might move on to say determine the intervals of increase or decrease and the inflection point. So now we need to look at the second derivative. Now remember, when we had taken the first derivative, we had really 2x squared minus x minus 1 over x. And to simplify our work, finding where f prime was positive or negative, we factored. I want to come back to the unfactored version personally. And the reason I want to do that is now to find f double prime, I have to use the quotient rule. Now what I personally don't want to do is use the quotient rule where I have a product in the numerator, right? Because when I do the quotient rule, I'm going to do bottom times derivative of the top. And I'm going to have to do a product rule if I use that factored form. So for efficiency, I'm going to use the non-factored form as I move through my product rule here. My quotient rule. So the derivative of the first derivative, right, my second derivative, I'm going to have bottom times the derivative of the top minus the top times the derivative of the bottom, and then all over the bottom squared. So let's do a little bit of cleanup here. So x times 4x minus 1 is going to give me 4x squared minus x. And then when I distribute this negative in the numerator, I'm going to get minus 2x squared plus x plus 1 all over x. And then I'm going to go ahead and do a little more cleanup there. Combining like terms, 4x squared minus 2x squared is 2x squared. And I get negative x plus x, that goes away. And then I get plus 1 all over x. So there's my second derivative. Now, to find, and this is not the proper term, right? I'm looking for the zeros of the second derivative. I call it the critical points of the second derivative, but that is horribly incorrect because remember, critical points are really just derivatives of f prime. So I'm finding where f double prime is 0, and I'm finding where it is undefined, because that could possibly be a change in inflection and maybe an inflection point. So where's f double prime equal to 0? Where's f double prime undefined? So I see in this case, where is f double prime equal to 0? That's actually going to be never, because where is x squared equal to a negative number? Never. At least not on the real number system. And then where's f double prime undefined? And that's going to be only at x equals 0. Now I'm going to be a little more efficient here. When I set up my line test and I'm asking for values of f double prime, what does that tell me about the original function? When I plot negative 1/2 and then 0, I don't really want to test negative 1/2 because it's not in the domain of my function. So only really want to test to the right of x equals 0. So I'm not even going to bother with either of those two intervals. So I'm only going to test here, let's say at x equals 1. So I need to come back up to my f double prime. I'm plugging into f double prime here, 2x squared plus 1 over x. So if I plug x equals 1 in there, I'm going to get 2 times 1 squared, which is 2, plus 1, which is 3. So I get positive 3 over positive 1. So I get positive 3 over positive 1. And my second derivative is positive. So my function is concave up. Now in this particular example, I don't have any other critical values. Only x equals 0. I don't have any other critical values out here. I'm never going to have a change in concavity, so I'm never going to have an inflection point on this function. So to summarize what we just determined, I'm going to say f has, or I'm going to say f is concave up on the interval 0 to infinity. We're never concave down, and we don't have any inflection points. So that finishes off this homework question. If I was being asked to find intervals of increase, decrease, max and min values, intervals of concavity, and any possible inflection points. This is really everything I wanted to discuss in this video. In the next couple videos, we're going to really take all of this information and do one last step. We're going to actually sketch a graph of the function. So in the next couple videos, we're going to do all of this work and then piece it together, sketch a pretty good detailed graph of the function, and at that point we'll take out our graphing technology, just kind of visualize and check our work. I look forward to seeing you in the next video.